Everybody get my message?
Yes.
Hopefully you did. Hopefully you're checking your email. If you didn't, hopefully you looked at your assignment sheet and it said to read that section on solving systems. And you've got the whole weekend, which is nice. A lot of times it falls where the test is tomorrow. So you do have the weekend to look over that, but I really wanted to answer questions today about that reading assignment. If you have any questions whatsoever, if you don't, I'm going to assume that you do, and I'm going to address a couple things that have hurt people in the past, mistakes people make in the past. But if you want to turn with me to your book, and maybe 37. Nope. Out of 49, maybe 45. Okay, so you'll see if you've read this already, great. If you understand everything, great. If you got a question right now, I won't even start talking. I'll just answer your questions. Anyone?
Can you just work through an example about the math team problems?
When you say math team, you're talking about the square root of the number one?
Yeah, the square root and then like the ax plus by.
Okay, absolutely. Any other ones? Okay, so I'll get there in a couple seconds, but just looking at this quickly, I would assume that you guys have no issues with solving a system using the elimination method. That's all I have right here, right? You try to make the x's match or maybe the y's match, eliminate an x, solve for y, plug it back in. I want to make sure that you understand that you can also do that even when it's not linear, even when it's not just x's and y's. If it's x squareds and y squareds, you can still make the coefficients match and eliminate them. The only difference is remember, you're solving for x and y, right? So if I eliminate those right there, I can still divide by a negative 11 or whatever, and I get to y squared. And when you square root both of those, what happens? You get plus or minus because that whole absolute value thing we've been talking about. And the plus or minus means you have two y values potentially. And those two y values are going to go with what? Most likely two different x values. So that means you could have potentially 4 points that make this true. You might only have 3 points that make it true. One of them might be imaginary and you have to throw it out. Maybe you only have 2 because 2 of them are imaginary and you throw those out. Maybe they're all imaginary and you throw them all out. But the point is, it's possible. Because what kind of a graph is that? This was actually a bonus. Now remember, what kind of graph is that?
Quadratic.
If you have an x squared and a y squared, you're subtracting them, but there's a negative over there. It's a hyperbola. Because if I divide by -6, all I got to do is end up switching the signs, right? So I have a hyperbola, and I'm trying to find the intersection points of a hyperbola with a, what is that? An ellipse, because they're both squared but different numbers up front, and they're both positive. So think about it. I could have a hyperbola. That's a terrible hyperbola. I could have a hyperbola with an ellipse and have 1, 2, 3, 4 solutions. I could have a hyperbola with an ellipse and have 2 solutions. I could have a hyperbola and ellipse and just have exactly 3 solutions. Or I could have a hyperbola and ellipse with 1 solution, or even no solutions. So all kinds of stuff's possible, but at most I could only have 4, and you can see that here. I got plus or minus 3. I plugged those 3's back in. I got x is plus or minus 2. And right here, you got to be careful when writing your answers because I need to write them as points. Okay? So just be careful when you do that. I want to know the points that actually make this true. All right? So right here, if I get a 3, for instance, a positive 3, if I plug it back in up here and solve for x, I get a, let's just do it. I should have shown that math right here. If I get a positive 3 for y and I plug it up here, that 3 squared is a 9. And I add that 18 and I get a what? Which means x squared is 4, which means x is. So when x was positive 3, when y is positive 3, I got an x that was either positive 2 or -2? That's 2 points. A +2 with the 3, a -2 with the 3. What happens when y is a negative? And I plug a negative in there and square it. Still 9, so I still get the same thing. Those are 4 points, right? The +2 with the 3, the -2 with the 3, the +2 with the -3, the -2 with the -3. But sometimes you get weird stuff like, sometimes you'll get y equals 2, y equals -2. And when you go to solve, when you plug this in, you might actually get something like x equals -1. You plug this in, you get x equals +1. Well, how many points is that? If that happened. 2. So do you see how it's bad to say, oh, if I say right here that x is -1 when y is 2, or 1 when y is -2, that's good. That's your 2 points. Why is this bad? Oh, x could be ±1, y could be ±2. Why is that bad to say that? It would seem like there's 4. Because when you look at this, you're like, well, I guess x could be 1 when y is those. X could be -1 when y is those. But that really wasn't the case. So be careful with the way you write your answers. And make sure that if you write something like ±2, if I were to write this, which would be okay here, if I were to write that, that means I have 4 points. If I really don't have 4, like in a case like this, where this only gives me one option, this gives me one option, then don't write it like this. This would not work for that. Are y'all seeing the difference? So that's something that happens occasionally on this work. I will promise you, you can expect at least one of the points to be really pretty. It's really hard to make these questions where all your answers look pretty. I mean, it's tedious to do that. Okay, so what one of them will. So if you get answers like x is 1, y is 2, and then you get something like x is 1/3 and y is 2/7, that's probably okay. But if all of your answers are complete chaos, like if your fractions are horrible, then you probably made a careless error. Maybe just go back and do the work and see if you can find it. Okay? And then now what happens in a situation like this? Yes, what happens in a situation like this? If that's squared and that's not, and that's squared and that's not, can I do the substitution method? Yes. Can I do linear combination? No. I have people all the time that go, well, why don't you just square everything? I would love if math worked that way, that I could just square each thing, but it just makes stuff not true. Like for instance, I know that's true, but if I go and square everything, is it still true? So me squaring it, it just doesn't make it true. I can't do it. And if I square both sides, that would give me an x squared and a y squared, which is awesome, but what does it also give me? That middle term with an xy, and then the lid's off, everything turns to chaos now. So in a situation like this, where you don't have a matching squared term, you're forced to suck it up and solve. I can tell you that I will most likely be a little kinder than this thing. That's pretty terrible to get a horrible looking fraction like that. But even if I wasn't, when you solve for x right here by adding it and dividing by 2, and when you plug it in and you square everything, at the very minimum, look, at least the 4's cancel nicely, right? And you are left with all this junk that when you got it all together and divided by 2, it's ugly, but at least it was kind of factorable. Are you seeing this? I try to do a much better job of I try to really avoid ugly quadratics like that. Make it where it's a little bit easier to deal with. But I noticed one of the y's was really nice, even though the other one was kind of gross. So that's going to happen from time to time, but I do my best to troubleshoot these problems so that when you're working on them, if you're doing them correctly, the math doesn't get just too bad. Are you with me so far? Okay, and then something like this, if I have an xy term or something like this, remember, don't forget what you already know. If it doesn't line up nicely and you don't have terms that are the same power that you can eliminate, just go back to your substitution method and be careful. But remember, when you do this stuff, very often you get multiple y values. For each y value you get, plug each one back in and solve for the x value. And by the way, if you have a choice, like right here, when I solve this, I got these 2 y values. Now, in theory, I should be able to take each of these, plug them in here, and solve for the other ones. Somebody tell me, why do you think it would be a better idea to plug, for instance, y equals -3 in here than plugging y equals -3 in here? Why is it better to plug it in here to find x? Well, that's true. The math might get uglier, but why is it really better?
Because the negative matters.
Like the negatives will make it a positive. X isn't squared. I don't know.
That's what I'm going for. Your statements aren't bad. I don't know. That's not like your answers weren't bad, but what I'm really looking for is if I plug a y in there, when I go to solve for x, it's just a single x, right? So it's only going to spit out one number. If I plug a y in there, it's an x squared. So when I go to solve, it's going to give me 2. What do you think that means if one equation gives me 1 and the other one gives me 2? One of those two isn't going to work, which means now you got to do what?
Plug them back in.
Now you got more work to do. You got to go back and check. So when it comes to solving that final variable and you have an option to pick which equation, always pick the equation with lesser powers. Because those extra answers are called extraneous roots. Sometimes they just don't work, right? So rather than I can avoid that step if I just go to the simplest equation with the least powers to plug stuff back in. Y'all seeing that? Yes? Okay, moving on to this. Right here, sometimes you have squared terms and squared and non-squared terms. Well, don't be freaked out about that. Because again, if I have matching powers, even though those don't match, I could eliminate the x's, right? By multiplying the top by a way to get the x squareds to cancel. Or if the y squareds are both, I could eliminate the y's. So look for opportunities like that. But don't make this mistake. Right here, when I multiply the top by -3, check it out. These cancel, but do I get -7y cubed? No, I can't add those. -6y squared and -y do not combine together into one term. So what do? I just bring them both down. There's nothing wrong with that. It's just something that you haven't seen a lot or maybe never. And then you add those together, and what do I have at this point? I have a parabola or a quadratic that I can solve. And yours will always factor nicely on this unit. So if you get to the point where you can't factor it at all, it might be because you can't factor everything really well. I mean, like you personally can't, but these are factorable answers. But most likely you made an error. So look for these to factor nicely. I don't like that negative there, so I multiply through by negative. But look for these to factor nicely. And you're going to get one answer that's probably pretty good and the other answer that's a little nasty. But I'll try to keep the factoring as pleasant as possible. If you need to use the quadratic formula, use it. And when you're done, you're going to get 2 and -13/6. And then take those y values and plug them in. And keep in mind, when you plug them back in, there's a good chance the y values that go with that, x values that go with it, look fine. There's a good chance that the x values that go with the other one don't look fine. So expect to see a little bit of ugliness out of one of the terms because it's really difficult to make these work out nicely for all the points. And again, if any point you can see over here, I could have rewritten this. I just wanted to show you the substitution method. To me, if I had that, I'm already solved for x. I can plug that right in there, plug it in there and square it. My powers get really big though. Have you seen that? I start getting some really big powers. When I solve, I got this ugly value right here. The nice thing is when I was solving this for this y, and I got down to here, everything I end up with from the quadratic formula, and this would have factored, it was just ugly, but everything I ended up with was negative. So what happens at this point when I square root both sides? Your y's are imaginary. Well, if your y's are imaginary, that's a gift because you don't have to do anything else. You're done. You don't have to plug that junk back in. You have non-real answers. But I think it might have been easier right here, maybe, if you just left or brought the y squared over to the left. Seeing that? And you could have just multiplied by a 9 and a 9 and a 9, and your y squareds cancel. And you get 9x squared plus 9x equals 10. You could subtract that 10 over, and now you're ready to start factoring, trying to get there. And again, if you don't know how to factor it, plug it in the quadratic formula and simplify. And whatever you get, whether it's real or imaginary, when you plugged it back in, you ended up getting imaginary y values. I know that because I've worked it a little differently. But look for the best way you know how to do it. And if you don't have matching terms and matching powers, you can't do the elimination. You're forced to do substitution. But you're going to get a random sampling of these questions. All right. The last one I want to talk about was, what do you do with 3 variable systems? Have y'all ever done these with Miss Tyree or anything? We haven't done matrices. Well, we have done matrices, haven't we?
Yeah.
And we did Kramer's rule.
Yeah, this one.
Okay, yeah, we just did matrices in pre-cal again. You'll do it again next year if you've forgotten everything you know. And you'll be really nothing new if you're in my class. We've already gone way beyond what's needed. Actually, I'll take that back. I show you how to do some things with your calculator, which is really great. Because your calculator has a lot of built-in things you can use. But so Kramer's rule I could have done to solve this. I'm not a huge fan of Kramer's rule. But another way you could do it is elimination. So if you have these set up like this, you can just pick a variable and say, you know what, I think I want to eliminate x's. I think that's what I chose to eliminate. So what I'm going to do is I've got to do basically 2 eliminations. I'm going to choose, say, equation 1 and equation 2. And I'm going to bring them down. And I'm going to try to eliminate x. And to do that, what does it look like I need to do? Multiply the bottom by 3, and I did that here. It gets me to here. And then I can eliminate the x, and now I have a new equation in terms of y and z, which I decided to simplify. Now, once I do that, I go back and do the same thing again with 2 different equations. It doesn't have to be 2 and 3. It could be 1 and 3. It just can't be 1 and 2 again, obviously. So I chose 2 and 3. So I took these 2, brought them down, and again, eliminate the same variable. Don't go, whoa, it's easier to eliminate z's. That's not going to help you. So whatever you chose to eliminate here, eliminate that same variable again. So I chose to multiply the top by a 2, and I got to here, eliminated the x's, combined it, and I've got another equation with y and z. And now I'm home free, because if I have 2 equations with 2 variables, what do? Solve again. So I took these 2, brought them up, and I looked at this and thought it might be easier to eliminate y. Multiplied that by a -10, eliminated the y, and solved for z. And once I get z, what can I do? Plug it back in one of these to find y. And once I get y, plug them both back in to one of these, and I can get my x. Now, is that process what you've learned before? Y'all seen that before? No? Does it make sense? Okay, with a little practice, you'll be in great shape. If you've already practiced a little bit, awesome. If you know how to do that, tell me what's the main difference between that, and this. This is on page 50. What is the main difference between what I just did and this? Fraction. So instead of the x being to the right of the number, it's below the number, right? So what? Can't you still eliminate something, whether it's, doesn't 3x and -3x cancel the same way 3 over x and -3 over x would cancel? Doesn't it? So don't let it bother you. Like a lot of people do these substitutions. They say, well, that 3 over a right here is really this. And they say, why don't we let 1 over a equal x? Then I can replace the 1 over a and I can rewrite that as a 3x. And they say, why don't I let 1 over b equal y? And then I can rewrite that as -2y. And they like making these substitutions like this, and they rewrite the whole thing in terms of x, y, z. And then it looks like the other problem. And then they get busy and they solve. And then what do you think they do at the very end when they make the mistake of forgetting to go back and figure out what A, B, and C are? I say, don't do any of that. Do this problem. Now, you see me doing it in my key right here, but I still think, because that's what you need to get introduced to substitution. But look how you could still do this and not do any of this substitution. Like, for instance, if I take these two equations, 3 over a minus 2 over B, 1 over C, negative 6. What could I do to this so that I could cancel out the A value? Multiply by 3, negative 3 over A, positive 9 over B, minus 15 over C, equals 90. So I chose those two equations and I multiplied the bottom one by a 3. Don't those two still cancel? What do you think negative 2b and positive 9b give me? 7 over b. What is 1c and negative 15c? And that? 84. Is there anything I could cancel out of this? Or divide out? 7 actually does. So I can actually get 1 over b minus 2 over c equals 12. And there's my b and c equation. Could I do this exact same thing with, say, these two equations? And eliminate the a by maybe multiplying that by a 2, right? So I do the same thing again, and then I get it down to 2 equations with b's and c's, and I can put those together and then eliminate the b's. And then remember, at the very end, you're going to get something like, you're going to get something like, what does it say the answer is, and I'll tell you. C ended up being negative 1/4. So at the very end, you're going to get something like this. C equals, you're going to get something like negative 4c equals 1 for the very last solution. So what do you do to solve for that? Flip it or cross multiply. You could either cross multiply and get c equals negative 4. You could flip both sides and then multiply by a negative 4, c equals negative 4. A lot of different things. But remember, your variables are on the bottom if you don't make that substitution. But if you like the substitution way, great. I think it's great either way. It just requires a little extra steps the way we did it here. All right, and then make sure I didn't skip something super important. Okay, this is a little math team trick problem. It shows up occasionally. I kind of wanted to show you. This problem has W, X, Y, Z, W, X, Y, Z, W, X, Y, Z, 3 different equations, right? You have these 3 different equations. Now, you could still solve this the way we just did. But how many groupings do you think you'd have to do since there are 4 equations? You'd have to do 3. You'd have to group these together and get rid of W, these together and get rid of W, and then these together to get rid of W to get 3 equations with X, Y, Z. And then once you did that, you'd have to group 2 of those to get rid of X and 2 of those to get rid of X to get down to YZ. Then you'd have to group those together and get rid of the Y to get to the Z. And then you'd have to start back substituting all that stuff in there, which is a lot of work, and I won't ask you to do something like that unless there's a trick. Like this. So when I see this, because I see these 3's running down through the diagonal, I'm going to use this little clever manipulation I have, which is, what if I were to just add all of them together? I get 6W, 6X, 6Y, 6Z, and whatever that sums to. And you can see that right here. And clearly, because they all have a 6, I can divide that through there, and I have the sum of the variables. And sometimes that's the question. They give you this and they go, hey, what's WX plus Y plus Z? Oh, well, by this little trick, WX, Y, and Z is equal to 2. I don't even know what the 4 values are, but I know that the sum of them are 2 based on the math I just did. Are y'all with me? Now, here's where it gets a little tricky. What if I ask for just W? Well, check it out. If I know this, and they gave me this, couldn't I take the WXYZ that I just found and combine it with this to find W? Like, what would happen right there if I took this value and I combined it with the one that had the 3W and I negated both sides? What happens to the X's, the Y's, and the Z's? They're gone, and I end up with what? 2W equals negative 3. And if 2W equals negative 3, I got my W. W is negative 3/2. And then couldn't I repeat that process and take the WXYZ equals 2 and put it with the second equation? If I wanted to find the x, negate the w, x, y, z, everything cancels but the x's, and I can solve for x. Everything cancels when I do it with the y term or the z term. And if I want to do individually, I can find each of those individual values. And that's how I found that, by just finding w, x, and y, z separately. So I wanted to throw that at you. That was just a little math team trick. Does that make sense, what I'm doing? If it doesn't, will you come see me? Let me walk you through it at a different pace. All right, last couple. And all I have right here is basically showing you that when you're solving a 3-variable system like that, what you're really doing is solving where do these 3 planes intersect. That's what you're doing. And how can 3 planes intersect? Like, think of a plane as this floor, this wall, and this wall. Where does the floor, that wall, and that wall intersect? At that one spot. Now, where do these 3 planes intersect? The floor, this wall, and the ceiling. They don't. That's a null set. Okay, that looks a certain way when you're solving. What happens if I have this floor, this wall, and then a 3rd plane that actually like is sliding right here through space and hits right at that corner? Then you'd have a whole line. Well, planes intersect in different ways like this. And I have some, where are they? Below or above? Above. And I gave you some of these pictures. A lot of times they intersect in a single point, but sometimes they intersect in a line, and sometimes they don't intersect at all. I mean, 2 of the 3 might intersect, but all 3 of them don't intersect in a similar place. So understand that as you're solving, sometimes you get situations where you go to solve. What if you're going to solve and all of the variables disappear and you get 0 equals 0? What do you think that means? It used to mean that they were infinitely many. There were an infinitely many number when you had 2 lines. The lines basically were the same line. But now it doesn't mean that. It means that you still have infinitely many if everything cancels and it's true, like 0, 0, 0, 0, 0, everything canceled out. But it just means that you intersected in an infinite number of places. But what if all the variables cancel out and you get something like 0, 0 equals see it right here. 3-variable system. I group these 2 together and I get rid of an x. Great. Then I group the next 2 together and I get rid of the x again. Great. Then I put these 2 together and I go to get rid of the y and everything cancels and I get this. That means that there are infinitely many solutions like this. Are you with me? And that they would all intersect in a line. All right. And I am not going to give you a question like this. This is more of a pre-cal topic, but you would have to find a way in pre-cal to describe what that line meant. But you don't have to worry about that on your quiz. Okay. And then same thing before. Did I give you an example? No, I didn't. But in that same example before, if instead of it giving you all zeros like this, if you went down to here and it went, well, y's canceled, z's canceled, and you end up with like 10, 0 plus 0 equals 10, that's a null set. But those you are not going to have to deal with. If I ask you to solve one on your quiz tomorrow, you will have a solution if I ask you to solve a 3-variable system. You with me? Okay. All right, last couple things, and you asked about these at the very beginning, these little math team questions. Okay, I want to show you something before I walk you through this. This is not a hard process. It looks awful. If you've read it and it makes sense, great. There are definitely shortcuts you can take, although I want you to understand the why. But right here, stay with me. Have you ever noticed that I'm just picking a random, you pick it. Give me a random imaginary number.
7.
Give me one that has like an A and a B part.
Oh wait, I thought you said a random number.
15 plus 4i.
You have to go double digits. All right, so 15
Really?
plus 4i.
Come on.
Notice that when I square that times that times 2, and then square that. When I simplify it, what do I end up with? Another a plus bi. So my question to you is this. If I can square an imaginary number and get an imaginary number, then doesn't it logically seem that I could square root that number and get back to the number it came from? That's what I'm asking you to do. The problem is, it's harder than it might seem at first. But I do know this, that if I square an imaginary and I always get an imaginary, then when I square root one, I can always get back to the original one. I just don't know what the original one is. But I do know that if it's imaginary, it's got to be what? In a plus bi form. So I'm going to say that this square root is equal, the square root of this imaginary is equal to some imaginary number. Does that make sense so far? Okay, now, we can square both sides, right? Sometimes that produces extra roots when I do that that aren't really true. In this case, it won't. It will on the other one. But sometimes that'll mess with me a little bit, but I can do that mathematically. So I'm going to square both sides, and in doing that, the square root goes away, and here I get a squared, that times 2, and then positive bi squared gives me what? B squared, I squared, which is negative b squared. That's why I have a negative b squared there. Now, here's where your logic comes into play. And you've done this kind of stuff before. Now, doesn't it make sense that if that is equal to that the imaginary part would be equal to the imaginary part, and that the non-imaginary part would be equal to everything that's non-imaginary? So, I write two equations that represent that. So I'm going to write negative 8 equals that minus that, and negative 6i equals that. And I'm going to solve the system, except it's easier than you think. Because a lot of people think to solve the system, they're going to have to do some crazy substitution. In 27 years of doing math team stuff, I've seen one question at the comprehensive level where the a and the b that we're solving for weren't nice, neat whole numbers. Just one. And that leaves dozens of others that weren't. So on these, what I like to do, rather than actually going and solving the system, is just doing a little guess and checking. Makes it easier, and I can find them more quickly. So let's clean it up what I got. First thing I notice is, if these both have an I can cancel that out. And that has a 2 always, because it's twice that times that. I'm going to cancel that 2 out. Now, make a little chart. What values of A and B multiply together to give me negative 3 that are whole numbers?
Negative 1, 3, 3, negative 1. Oh, wait,
So
negative
1 and 3.
Negative 3, 1.
Negative 3 and 1. That it?
Yeah.
1 and negative 3? 3 and negative 1?
Yeah.
Y'all with me? Now, which of those, if I plug them in here for A and B, equal negative 8? Negative 1 squared gives me 1. 3 squared gives me 9. That's true. But look, if I plug negative 3 in here and 1 in there, that's not true. In fact, if it's not true there, where is it else not true? But is that true?
Yeah.
Now, what are those right there? What is that? I just solved for what?
A pair, order pair.
Of A and B?
Yeah.
And what was my goal in this problem?
A and B.
Nope.
Wait.
To find that imaginary number? So what are my imaginary numbers?
1 minus 3a, negative 1 plus 3.
Negative 1 plus 3i and
1 minus
positive 1 minus 3i. If you don't believe me, square them. I bet you get negative 8 minus 6i. Y'all seeing that? Not too bad? Let me show you the radical stuff. And by the way, these can get much worse than what I'm showing you here. This is a child's play at this point because the radical on the 3, it's a 3. All I got to do to mess with you is make it where it's not a prime number. And it really becomes tricky. And again, that's more of a pre-cal topic. If that shows up at a state tournament, whatever. Okay, but it's more of an ugly pre-cal question. Most of the time when you see these, this is not the case. But let me show you. The same thing is true for imaginary numbers as square rooted values. Like if I have 2 minus root 3, heck, I'll even put a 5 in there for fun. What happens when I square it? I get 4. That times that, negative 20 root 3. That squared, positive 75. I get 79 minus 20 root 3. So if I can square a number that's kind of like a whole number and then a radical number, and still end up with a whole number and a radical number, doesn't it beg the question that I could square root this and get back to where I started? Yes, no? So with that in mind, if I ask you to square root a number like this, I'm going to assume that when I get done with it, it's still going to be some number plus some other number root 3. And you saw that here. A number plus maybe minus some other number root 3. You seen it? Now it's the exact same process with one small tweak at the end. All right, here we go. Square both sides, square that, outside square root goes away. Square this, square the x, that times 2, and then square that gives me y squared times 3. Are you with me so far? Everybody? Does it feel the same so far? Except you didn't have an I in there, you had a root 3 instead of an I. Now, if this is true, what can I set equal to each other? There's no i's, but there's roots, right? So could I set the stuff that has the roots equal to each other? And then the stuff that doesn't have the roots equal to each other? And then just like I did before, instead of canceling out the i's, I cancel out the roots, right? And while I have that 2, might as well divide it out also. And then you're solving a system. That's why it's in this little section. Except we're not going to solve the system because we're going to assume first that there are whole number answers to this. So this one's a little bit maybe more involved. So let's go, what values of x and y give me negative 10? I could have what? 1 and negative 10, or negative 1 and positive 10, or 10 and negative 1, or negative 10, positive 1, or negative 2 and 5, or
Positive 2, negative 5.
positive 2, negative 5, or
Positive 5, negative 2.
5, negative 2, or
Negative 5, positive.
negative 5, positive 2. So a little bit more to check. So let's roll over here. Start. If I plug a 1 there and a negative 10 there, am I getting 37? If I plug a 10 there and a 1 there, am I getting 37? If I plug a 2 there and a 5 there, am I getting 37? No, because the 5 squared times 3 is already 75, right? If I plug a 5 there and a 2 there, am I getting 37? 25.
Yes.
Negative 2 squared is 4 times 3 is 12. That works. And what else?
Negative 5, 2.
That works. Now, here's the one thing you got to be careful about. You would think if those are your x's and your y's that you could come straight up here and say 5 minus 2 root 3 and negative 5 plus 2 root 3. Here's where you got to be careful. Somebody tell me approximately what 5 minus 2 root 3 is equal to.
About 1.5.
How do you figure? Walk me through it.
Okay.
I'm gonna go with
It's about 2.
The root 3 is about what?
1.7.
1.7. Again, it's good to know that because it helps in situations like this. What's 2 times 1.7? Like 3.4-ish? What's 5 minus 3.4-ish?
I'm gonna go with
1.6-ish? So that's about a 1.6-ish. Is it possible to square root a number and get a positive 1.6? Yeah, you can get positive numbers when you square root. What was this equal to? This is negative 5 plus 2 times 1.7. What's negative 5 plus 3.4-ish? Negative 1.6-ish. Wait, is it possible to square root something and get a negative? No. Now, if you're wondering, well, why didn't I have to think about that with imaginaries? Well, imaginaries are neither positive nor negative. They're imaginary. Think of pretend. right? So you don't have to worry about that with imaginaries, include them both. But on these, can't include them both. And if you're ever wondering what you would have to do if that number 3 was not prime, which yours will be prime if I give it to you, if it was something like 6, then it's possible that you rewrite this as x plus y root 6, but you might also have to write it as x root 2 plus y root 3. And you won't know. So you'll just have to guess and check and revise until you finally get something that works nicely, which is not fun. But that's pre-calc. Actually, that's math team pre-calc. Pre-calc doesn't make you do this. I don't even, this is in your book, believe it or not. Your book has to talk about the imaginary stuff. I don't think a modern textbook would have, because sadly we've dumbed down math over the past 30 years. Not in here. It's only gotten more rigorous.
Yes, sir.
Yeah.
Like I taught, I've taught a couple people's parents over the years, and it's been a long time. But over the years, just what I did in 1996 is a lot different than what I'm doing in 2020. Just a lot. I've just learned more, so I throw more at you. Some of you are like, man, I want the 99-6 course. I hear you. Is this making sense? Okay. Got a quiz on Monday. All right, we have some classwork that we don't really have time to do right this second, maybe 8 minutes. And then there's also a review sheet. If you look at this review in here, this is basically what your quiz would look like. You're going to have probably a problem that has 3 variables and 3 equations, whether it's like that or whether it's a reciprocal, I don't know. You're probably going to have something like this where you have a conic situation where they're both squared, or maybe where they're squared and then not squared. Probably have a situation where you have to do a substitution, maybe where one of them's squared, one of them's not, right? So these could probably be eliminated nicely, but those wouldn't. And then you'll probably have something, maybe a problem like that, like the trick problem I showed you, and then maybe one of these with the eyes or the roots. And it really will probably look this length. It shouldn't take you the whole period, although I'll give it to you. And that'll be it. So it's probably like if it had 7 questions, it might be a 35, 42 point quiz or something like that. Not a 100-point test by any stretch. Maybe even a little smaller than that, I don't know. Y'all seen it? So practice these up. You got plenty of practice, I think, if you do the review and you do the classwork problems. And if you really need me at the last second, I'll let you come in on Monday and ask questions, since we really haven't had a whole lot of time. Or you can drop by after school.
Mr. Hurry, are we supposed to turn our reviews in from yesterday?
No, I don't want.
Yeah, and there's no difference. Please don't. Because I told him that after she's done. I'm trying.